So I have a lot simpler goal for this talk, which is to give you some understanding, some motivation for ETH and strong ETH. And I'll have only a few slides talking about the consequences, and they will be elaborated upon during the rest of the 4 days. So that part will be minimal. Okay. But before we get to understanding to understand the motivation for ETH, I need to take you through a quick trip of exponential time algorithms for NP-complete problems. And you have seen satisfiability algorithms this morning, and I'm going to broaden it a little bit, and Thor is going to kind of expand upon that and talk about the details. Okay. And bullet 4 will not be talked about, so that's so the main, when okay, sure. So the phenomenon, okay, so let me start with a kind of observation, and we know that all NP-complete problems are equivalent as far as polynomial time reducibilities are concerned. So that means if one is solvable in polynomial time, then everyone else is. Okay. But on the other hand, if you focus on and if you don't believe that P equals NP, and if you see that as a remotest possibility, so then you would start wondering about what is the exact complexity of NP-complete problems, and then you start noticing problems vary widely in their complexity. So before I go, let me define what exact algorithm means. So it's either a deterministic or randomized algorithm that produces exact solutions. So that's the definition. And we are focusing on the worst case complexity as opposed to average case complexity. So those are the two stipulations. So we could ask a similar question as that of similar to the one we asked for satisfiability. What kind of improvements can we expect over exhaustive search? But one caution we have to take is that what exactly is the complexity parameter here? In the case of satisfiability, we kind of implicitly or naturally assumed the search space is 2 to the so the search space is 2 to the n, which is the set of all possible assignments, and therefore we took n as the number of which is the number of variables, as the complexity parameter. So then we were looking for improvements over that. Okay. But in general, it may not be clear what's a natural complexity parameter. So we're going to leverage that out, and we're going to define problems together with the complexity parameters. So then talk about improvements over so with respect to the complexity parameter. So one way to think of the complexity parameter is that it could be the size of the search space, or the log of the size of the search space, and or something else that has a good motivation. Okay. So if we can find improvements over exhaustive search, what are the obstructions to the improvements? So these are the basic questions. We see a variety of complexities, and so we want to improve upon exhaustive search, and the last one is an ambitious question: what principle will explain the various complexities? So can we come up with a small set of principles that will explain the exact complexities of most of the interesting problems? Okay, so these are the meta-level goals. And so let me go through the definitions. So problems come with two things. One is the size of the instance, and the second one is the complexity parameter. Okay. And so for example, KSAT formula, you have the formula size, which is the number of clauses or the number of literals, and the number of variables. One can take number of variables to be the complexity parameter. In this case, it measures the size of the search space, or one could also take the number of clauses as a complexity parameter. So it's whatever you want to take as a complexity parameter. So basically, problems will come together with a parameter. So that's the framework here. So for example, for a Hamiltonian path, you take the number of vertices as a complexity parameter, or you can take the log of the search space. So you have n factorial permutations of the paths. Of the paths that encompass simple paths that encompass all vertices, so you can take the log of that as your parameter. Okay. Or some more examples, you can take the circuit SAT, and circuit size is the size of the instance and the number of variables. Or more generally, you can look at the class NP, and you can look at the number of the circuit size as a parameter, and the number of existentially quantified Boolean variables as your complexity parameter. So this is a fairly natural parameter, so that measures the set space. That measures the set space, and moreover, with this parameter, so you can reduce every other problem in NP to the circuit set problem without increasing the parameter size. So once we have the parameters, so previously we are focused on preserving the size of the instance within polynomial bounds. Okay, now we are also interested in preserving the complexity parameter within some bounds. Okay, so circuit set is a good problem, or the mother of all problems, because it preserves the complexity parameter. Okay, so now we can define what we mean by kind of improved, kind of exact algorithms over exhaustive search. Okay, so if n is the parameter, complexity parameter, poly of the size of the instance times 2 to the n is the kind of exhaustive search. And if you can improve upon that, so that's called an improved exact algorithm. Okay, so mind that this is so this improvement is with respect to the parameter. So for example, that okay, I'll give a number of examples of improved exponential time algorithms for NP complete problems. So 3 SAT, that's the best known constant, and with complexity parameter being n, so that's an improvement. Same thing for 4 SAT, and more generally for k SAT, we have that kind of improvement. Okay. So similarly for k colorability, so we had improvement up to 3 and 4, and so over exhaustive search, where you take the number of vertices as the complexity parameter. So Hamiltonian path has a more interesting history, or equally interesting history compared to colorability and 3 SAT. And the first algorithm, which achieves the 2 to the n bound, can be viewed as an improvement over the parameter log n factorial. So basically, exhaustive search may require you to go through all permutations, and the very first dynamic algorithm or inclusion-exclusion algorithm can be viewed as a significant improvement. And even if you take the number of vertices as the complexity parameter, so we were able to improve, and so that's the most recent result, if I'm right. And so that's the state of the art for the Hamiltonian path problem. Okay, to give you some more examples. Okay. Right. Okay, so if we take, okay, so this is an example where we don't have an improved algorithm when you take the number of vertices as the complexity parameter. So the best algorithm we know is 2 to the n time and in exponential space. Okay. I'll get to that a little later. So let me skip independent set. And and if you look at circuit SAT, so there are, for the more general circuit SAT, we don't know of any other algorithms better than 2 to the n. And if you look at special cases, so we have a variety of algorithms due to a variety of people. And I'm sure Ryan will talk about ACC satisfiability subsequently. And we also have improvements for depth to threshold circuit satisfiability. So this is just a quick rundown of a class of algorithms for which we have improved algorithms, for which a class of problems for which we have improved algorithms, so with respect to certain parameters. So this raises a number of questions. This is the starting point for thinking about ETH or for motivating ETH. Okay. So which problems have improved algorithms? Okay. For example, we know that KCNF has improved algorithms when we take the number of variables as a complexity parameter. But on the other hand, if we take CNF SAT, we know of no improvements. Okay. Similarly, colorability or chromatic number, so the best we know is a 2 to the n algorithm, and this is not an improvement when we take the number of vertices as a complexity parameter. Okay. When we have improvements, can we expect more and more improvements? So 3SAT, people have tried for a long time, tried to improve it, and there have been a sequence of improvements. Unfortunately, the progress stalled at 2 to the 0.386 times n, and so can we expect to improve it? And if not, why not? And the same thing for 3 colorability. So there have been a series of improvements, and the progress has stalled. Okay. So if we can't improve it, can we prove that improvements for 3SAT beyond a certain point are not possible, are subject to certain complexity assumptions? So we don't know how to do that either, and perhaps we can aim lower, and can we connect the progress on various problems together? This improvement on a continued improvement on 3SAT and continued improvement on 3 colorability may be related. So if we can establish that, that could begin a complexity theory of exact algorithms, and that's the starting point for this theory. Okay. Yes, ideally, we would like to answer the first question, and so we will settle for the last question and try to see whether there are connections. So one thing I do want to say is a lot of effort has gone into these algorithms. Thor will explain it further. And a variety of techniques have been used. And this is a kind of productive area. So new techniques have been developed. And different or clever analysis have been developed. And so this led to, so this is a, maybe 15 years of work led to several textbooks. And that's a good thing. So what we are focusing on is that can we find some principles that govern these complexities? And so we'll focus on the simplest of these questions. Can we connect various complexities? Okay. So for example, 3 colorability versus 3SAT. So for example, if 3 colorability has a sub-exponential time algorithm, by that I mean 2 to the epsilon n algorithm where epsilon can be made arbitrarily smaller, does it imply a sub-exponential time algorithm for 3SAT? So this is a concrete question to motivate the ETH and Sparsification Lemma. So what's the obstacle in proving such a result? So you can take the standard reduction, reducing 3SAT to 3 colorability. Okay, so if you take the standard reduction, so this is how the reduction works. So you take a 3SAT on n variables with about n cubed clauses, or with m clauses, and you reduce it to a graph with n plus m vertices and about n plus m edges. So if we take the number of variables and the number of vertices as the complexity parameter respectively, so the complexity parameter is blown up. For a man, it becomes n cubed roughly. And since we did not preserve the complexity parameter, so even if 3 colorability is solvable in 2 to the epsilon n time for arbitrarily small epsilon, that would not translate into a similar algorithm for 3SAT. So we're kind of stuck here. Okay. So so let me talk about the most important tool, or the tool we found most useful to lift us out of this dilemma, and that tool comes in the form of this Sparsification Lemma, and there are 2 concepts that are important, and one of them is sub-exponential time reduction. But let me restate it. It's the same lemmas as this morning, and in sub-exponential time for any given epsilon in 2 to the epsilon n time, we can rewrite a KCNF with an arbitrary KCNF as a disjunction of linear size KCNFs, such that the solution space is preserved, and that's the strongest statement you can make. And okay. So let me show you how with this lemma that we could lift ourselves out of the obstruction we faced earlier. Okay. So let's continue with the same proof. Okay, let's look at the reduction from 3 SAT to 3 colorability, and we want to preserve the linearity in the parameter value. So why is that? So the argument we want to make is that if 3 colorability with the number of vertices as a complexity parameter is solvable in sub-exponential time, so we would like to conclude 3 SAT with the number of variables as a complexity parameter is also solvable in sub-exponential time. And such a conclusion would be possible if we can do a reduction from 3 SAT to 3 colorability where the complexity parameter is maintained, where the complexity parameter is preserved so linearly. Okay. So now you see that is possible. So we start with the 3CNF, we apply sparsification lemma. So okay, we choose an epsilon, we apply sparsification lemma. Now we have 2 to the epsilon and sub-instances. Okay, for each instance, and each 3CNF instance has a linear size. Okay. Now we take that linear size 3CNF and convert that into and reduce it to a graph with linearly many vertices and linearly many edges, such that the 3CNF is satisfiable if and only if the corresponding graph is 3 colorable. Same standard reduction, but we restrict it to sparse KCNFs or sparse 3CNFs. Okay. And so we preserve the linearity of the parameter, and so therefore now we can conclude that a sub-exponential time algorithm for 3 colorability implies 1 for 3 SAT. So that's where the kind of sparsification lemma kind of occupies a central place in making these parameter preserving or linearity preserving reductions. And so if you think about it, I'm not going to go into the sparsification lemma proof, and so that the 2 key things that work as, of course, apart from a clever argument, sub-exponential time reductions, and so that's the key to our key flexibility we have. We can spend a sub-exponential amount of time. So the lemma itself comes from a branching program. So you branch on clauses and try to balance both sides, and so try to control for the number of leaves you get in this process, and without branching too much, so you can get linear size formulas. So then you are happy. So that's a very high level. Okay. So we are able to connect to canonical NP-complete problems the progress with respect to kind of improved exponential time algorithms in the natural complexity parameters. So it turns out this is the key for a much larger class of results, and let's take a subclass of NP-complete problems. I call that SNP. I'm not going to. So the definition is whatever it is. So you have a second order quantifier, existential quantifier, followed by a first order universal quantifiers. This subclass includes problems like KSAT and K colorability, and so that's an example of how you could express KSAT in that model, and it also includes problems like vertex cover, clique, independent set, and KSAT cover in the so-called size constrained SNP. So we restrict the size of the solution, and problems like Hamiltonian path are SNP hard. So the main point is that for this subclass of NP-complete problems, so they're naturally reducible to KSAT. So therefore, if you understand KSAT, so we can now deal with all the class of problems. Okay, so this is the main result, and so 3SAT admits a sub-exponential time algorithm if and only if one of the problems in SNP admits one. Okay. So we connected a whole bunch of problems together. So the possibility of sub-exponential time algorithms is kind of intimately linked. So they're all linked together. Is it 1977? 1997. Yeah, I should not go back in time, I guess. Yeah, I cannot go back in time. So I didn't even know what complexity is at the time. I think that's when I started programming. Okay, so let me give a sketch of the proof, so basically every problem in this class is reducible to k-SAT. Okay, and we are going to show that sparsification lemmas allows k-SAT can be reduced. So k-SAT can be reduced to 3-SAT while preserving the complexity parameter. So let me spend a minute talking about the standard reduction that we use from k-SAT to, from 4-SAT to 3-SAT, for example. So you have clauses with four literals. So you want to take such a formula and reduce it to a formula with only 3 literals per clause. So the typical thing is that you will introduce additional variables. So rewrite the clause as a conjunction of shorter size clauses. The number of clauses you introduce, the number of new variables you introduce is proportional to the number of clauses. For each 4 clause, you may have to introduce 1 or 2 new variables. Okay, I guess 1, yeah. And if you have n to the 4 many variables in a 4CNF, that requires you to introduce n to the 4 many new variables to reduce it to a 3CNF. So doing so, you're not preserving the complexity parameter linearly. So therefore, you cannot draw useful conclusions. But on the other hand, with the sparsification lemma, you can take a KCNF, and in sub-exponential time, you can reduce it to a linear size KCNF, then reduce it to a 3CNF by introducing new variables, but only linearly many new variables. And so therefore, while preserving the parameter, which is the number of variables, so we are able to go from an arbitrary problem in SNP to 3-SAT. Okay. Once again, sparsification lemma is the key. Okay. And so that shows if 3-SAT can be solvable in sub-exponential time, so then the whole class is solvable. Okay, so that's basically the, okay. So that gives you some motivation to make a hypothesis, and of course we don't know whether 3-SAT is solvable in sub-exponential time or not. I don't think neither Russell nor I have a bet on that, and we thought it's useful to come up with a hypothesis and kind of bifurcate the world into 2 worlds. Russell likes many more worlds, but okay, we have a world. So we are going to. So let me introduce one notation which will be useful down the road, and for each k-SAT, for each k, so let's introduce a number called S sub k, which is the best constant for solving k-SAT. So using an exact algorithm, which could be randomized. So let's say Las Vegas type algorithm. So ETH basically is that S3 is bounded away from 0. So that's exponential time hypothesis, and so subject to this hypothesis, every problem in SNP, no problem in SNP has a sub-exponential time algorithm. Okay, with respect to the natural complexity parameter, which is the size of the second order quantifier.
SNP or in P too, right? So you mean like a certain class of SNP hard problems?
Sorry, yeah, right.
So, but what class is that precisely?
So these are the NP complete.
SNP problems.
Yeah. I think SNP itself is defined as a subset of NP complete problem. No, sorry.
Are all NP hard problems also SNP hard?
So
maybe
So if you assume, so the standard proof of the dichotomy theorem, then every constraint satisfaction problem is that's not in polynomial time is NP complete under gadget reductions. And for every one of those problems that's NP complete under gadget reductions, you can show that it's in sub-exponential time if and only if three sets in sub-exponential time. So in that sense, and basically every NP complete problem that you know of in SNP is complete under gadget reductions. And the conjecture is that all of them are. So pretty much every problem that you can think of is equivalent to 3 SAT for having sub-exponential time allocations.
Okay, so one small perspective is the following thing, and so we know very little about exponential time algorithms. In the sense, and we know very little about nonlinear time, what we can do in nonlinear time. So, proving time lower bounds has proved to be illusory. Okay, so one way to judge the value of ETH is that can we take this principle, can we take this hypothesis and try to explain the complexities, try to prove lower bounds that match the best known bounds. So that might serve as a justification for ETH, or the value of the ETH. As subject to this hypothesis, at least we can explain the known complexities. So, and maybe that's how we can judge any of the of course, any of the hypotheses we make. So the thing is that, so does ETH factor out the essential difficulty of dealing with exponential time algorithms? Perhaps not. And it only deals with one aspect of the exponential time algorithms. Perhaps more principles are needed to understand the set of exponential time algorithms for NP-complete problems. So, so this is one principle that proved to be useful. So that's my kind of high-level perspective about. So this kind of invites maybe we need more. So even if we can't understand time, so we can try to figure out what are the right principles we can use to explain the rest of the principle. To explain the rest of the facts. And it's not clear what those principles are, and they need to have a lot of explanatory value to be useful. And I'm sure Russell will talk about non-deterministic strong ETH.
Not in this week.
Okay. So let me quickly go through a couple of slides of some of the consequences. So, so there's a nice survey paper by Daniel and Saket, so let's look at special cases for planar graphs. We know that 2 to the big O of square root and algorithms exist, and kind of ETH removes the possibility of 2 to the little O of square root and algorithms. And for FPT problems, this also rules out the possibility of 2 to the little O of k times poly type algorithms for many problems. And for W1 complete problems, it kind of eliminates the possibility of n to the little of k type algorithms for a clique or independent set. So, so the best known algorithms have the form, f of k times n to the k, and ETH rules out the possibility of n to the little of k algorithms. Similarly, for dominating set and problems that are parameterized by tree width. Okay, so Daniel Marks will go in detail into these things. I'm just flashing the results, and So basically, for many interesting problems, sub-exponential time algorithms have been ruled out, so using ETH. So that's the kind of high-level summary, and Daniel will talk about some of the reductions. And okay. So one thing you notice with ETH is that we don't have any, so the kind of results or the kind of lower bounds are of the type 2 to the little of n, 2 to the little of square root n, or 2 to the little of k. We are not able to show that you need 2 to the k times poly n for a particular problem, and you can prove precise exponents. Of course, our assumption ETH itself is not precise enough. It simply says that S3 is bounded away from 0, and we don't know what that constant is. So even with respect to that constant, can we prove some lower bounds? And it's also not clear how to do that. So, and we went in a different route and proved a somewhat different results. So let me kind of focus on one of the interesting lower bounds we obtained by using ETH. Okay. This has to do with the complexity of the KCNF as k increases. I define this constant S sub k, which is the best exponent for the complexity of k SETH. And so what can we say about this sequence of constants assuming ETH? So what we show is that it is increasing infinitely often. So this sequence. Okay. So let's define the limit of the sequence to be S infinity, and so we not only, and we also show that the gap between the limit and S sub k is at least d over k for some absolute constant. So we have some idea about how it is increasing, so basically, assuming ETH, we can kind of say why the heuristics for that work for 3 SETH may not work that well for k SETH, because complexity has to necessarily increase, of course, assuming ETH. Okay. So here we take the leap. Okay. So let me give you a proof of this result, and kind of how do you show that the complexity or the constants S sub k are increasing infinitely often? So the idea is a kind of self-reduction, and so we take a KCNF, and we reduce, and using sub-exponential time, we reduce it to k prime CNF, okay, where k prime is much larger than k, and of course it's a Turing reduction. And while doing that reduction, we are going to exhibit an interesting trade-off between the clause width and the number of variables. So k prime is much larger than k, so we have more expressive power. So we want to exploit that expressive power, and in the trade, we would like to reduce the number of variables. So to go back to, so let's for a minute assume that so the k SETH has at most one solution. Okay. So we already show that this morning that roughly n over k variables are forced. And maybe we can eliminate those variables as a consequence of knowing the other variables. So those variables can be functions of the other variables. Can we use the expressive power of this? So these larger width clauses to eliminate those k variables. So then we can achieve the trade-off. So reduce the number of variables and increase the width. So then we get a connection between S sub k and S sub k prime. And that's the game plan. And so that's basically the proof sketch. Okay. So certain variables are forced, and which variables are forced can be guessed or can be determined by looking at locally. Okay. But to be able to do that, one need to have the locality, and that requires sparsification. The sparsification guarantees no variable occurs in more than k to the k many clauses. So the influence of the variables is somewhat limited, and we can take advantage of that to express this dependency, so using larger clause width. Okay, sparsification lemma is crucial for this result, and so we can establish, so using a variety of techniques, we can establish that this constant keep increasing. Yeah.
Do we have any information that says that the constants increase somewhat quickly to S infinity, something in the opposite direction of this? Like, is there any computable, lower bound on the rate of convergence to the limit?
It follows from.
So the gap is d over k. So if you
No, he's asking what's the smallest L so that we know that SL is bigger than SK. And we compute that L, but it depends on the actual limit constant, okay, what S infinity really is, and and then we have to use sparsification with the epsilon and the sparsification less than the limit constant.
Okay.
so k prime is at least k to the k or larger.
Order of exponential, and something like k to the k.
Okay. That's interesting. But what I was actually asking is, like, suppose that S infinity is 0.1, and we want a k large enough so that it's so that S of k is within epsilon of 0.1. Can we find a computable k for that?
Second bullet should give you a gap between the two things.
No, that's the other way.
The other way.
So that I don't think we know.
Okay. Yeah, equality. No, we don't.
Yeah, and in fact, that would be really interesting is if we could show you can't converge to S infinity faster, since that would say, for example, if strong ETH is true, if we had the direction the other way, then then you can't have an algorithm that's of a different form than a order 1 in k savings. And we don't know that.
The technique for showing 4CNF to reduce 4CNF to 3CNF introduces far too many variables. It's not clear what the trade-off is. So we'd like to introduce few more variables. So you want to do the trade-off in the reverse direction. So let's say you want to go from 4CNF to 3CNF. So let's say 1 in k more variables. Can you shrink the class width? And we don't know how to do that. That will give a kind of nice result. So let me skip over this one. Okay. So we know that this sequence is infinitely increasing, so thanks to Ryan, we know that who tried very hard to come up with a faster satisfiability algorithm for CNF SAT. So we got the courage to take a leap and say that this limit is 1. Okay. So there are two pieces of evidence. One is that if you look at the best satisfiability algorithms for KSAT, so they behave like 1 minus 1 over k. So the dependence on k seems to be there. If you go in the limit constant is 1. But independent of that, right. So this is not a rational justification. So this is a kind of justification why we made the leap to believe that S infinity equals 1.
We also assume that, we also assume the exponential-time hypothesis for this, right? Like we have to assume S of 3 is greater than 0, and because if we
this implies strong ETH implies ETH. So you can go from KCNF to 3CNF. So if the limit is 1 for some concrete k, so it is at least 0.9. Okay. From that you can go to 3CNF, reduce it to 3CNF, and so then you know that S3 must be.
Okay, sure.
So this is a stronger hypothesis, strictly stronger hypothesis. And we don't know how, okay. Of course, an interesting question is that can we prove this using ETH? That will reduce the number of hypotheses required, and that's a good thing, definitely a good thing. And that will be, so that will be a tremendous result, and we all should look forward to that result. So this kind of explains that we don't understand exponential time, and we need more principles. So this kind of came naturally. This is kind of adjacent one, and okay. So right. So let me give a kind of different kind of evidence and it turns out that the best constants for a variety of problems are related as well. Okay, so there's a paper where we look at a number of natural problems like a k-set, k-hitting set, k-set splitting, and so on. So either they all have the constant, so they have their best so their limit constant as 1 or strictly less than 1. So it cannot be that the limit constant of k-hitting set is less than 1 and the limit constant of k-set is equal to 1. So this is some more indirect evidence that the fate of all these constants, as far as being equal to 1, is kind of linked together. So they're all less than 1 or they're all equal to 1. Okay, so let me give you a few results quickly that follow from strong ETH. There are many more results, and so you will see. So you will notice the precision that we were able to achieve in terms of lower bounds. So, for example, for independent set parameters by tree width, so the result that you need, so 2 to the tree width rather than 2 to the little of tree width. Okay. So dominating set parameters by, so a tree width again requires a 3 to the 3 width. So we're able to obtain precise constants in exponent subject to strong ETH. Okay. So Daniel Marks will say a lot more about it. So let me say Virginia is going to have a full series of lectures on this topic. I just will mention a few things that were in my slide before. So it also says, okay, strong ETH, not so surprisingly, seem to say something about the complexity of problems in P. Okay. So one problem is orthogonal vectors. So you have a bunch of vectors, okay, 0, 1 vectors, so over integers, let us say. So you want to check whether there are 2 of them that are orthogonal to each other. Okay. And Williams has shown that that cannot be solved in strictly subquadratic time, unless strong ETH is false. And more recently, we have a similar flavor problem. So you have a bunch of real vectors. You want to know whether there exists a pair of them such that one dominates the other component-wise. Okay. So this, again, cannot be solved for sufficiently large dimension for when the dimension of the vector is omega of log n, and where n is the number of vectors. And so this is the only last result I will mention. And Carl has shown that fresh air distance, which is a problem that requires dynamic programming. So I typically use a dynamic programming technique to solve it, seem to require strong ETH rules out strongly subquadratic algorithms. Okay. So many others, and Virginia will give a full version of this slide, and many more things. Okay, so let me skip over all these things, and okay. So let me mention some open problems. Of course, before that, I have to say that these seem like hard problems, but on the other hand, not many people have thought about them. It's possible that they have easy solutions or somewhat easier solutions. And assuming ETH, can we prove a specific bound on S3? Okay. Or assuming ETH, can we prove S infinity equals 1? So these are 2 questions I mentioned. Okay. And so this one is an interesting question. Okay, so you have strong ETH, let's assume that, and that tells us something about the complexity of CNF SAT or the limit constant of the KCNF K-SAT exponents, can we say something about the colorability? Does it require 2 to the n time? So does improving one help improving the other? Okay. Or can we rule out a reduction between the 2 types of problems? So the best known algorithms for K-SAT seem to use a branching style techniques, and whereas colorability seem to require inclusion-exclusion principle. It may be there's no reduction between these problems that preserve the exponent. So that seemed to showing something like showing the impossibility of a reduction. So that will be definitely interesting. Or there's a reduction between these 2 problems. So that will be great to know. So then we can reduce the number of principles we need to understand the colorability problem. Let's skip that one. Let's skip that one too. Okay. So these are part of the talk I skipped, but so the first 2 are we should be able to make a lot of progress if we could say something about the first 2 questions.
So there was a tradition in the crypto program to offer small monetary rewards on the scale of like the Erdős prizes for your open problems. So which ones? How much money would you be willing to pay for these 2?
So proving that S infinity equals 1, assuming ETH, I would put a high dollar value on that.
How much?
500.
There we go.
No, this is my. This is not about money. So this is about my judgment about the difficulty of reasoning about time.
And now we have a normalizing constant.
So for the second one, or at least connecting CNF SAT and colorability, I don't know. I will not place more than $50. So even ruling out the possibility of such a reduction. Both are equally interesting, and I mean, one dream here is that somehow can we classify the NP complete problems kind of in a more fine-grained fashion. So these are the problems that require DPLL style algorithms, and to obtain the optimal algorithms, of course, subject to assumptions. These are the ones that require inclusion-exclusion, and reductions among them are not possible under reasonable assumptions. That kind of classifies or stratifies the space of these problems, and that's definitely progress if we can do that. And the same thing applies for quadratic or cubic complexity problems. So Daniel, are you saying? Hi, Paul.
So in ETH you had these, the SMP or some SNP. Is there any kind of rule of thumb for understanding any other larger part of the space? There were a lot of FPT type consequences of some of these assumptions, but what do we know sort of more broadly? Are there any sort of broader classifications?
So you are looking for a larger class of problems for which we could tie that.
For ETH, how do we judge a problem to suggest whether it's going to be in the?
So okay, that's just a kind of question here in the sense. So let's say we have strong. Okay, for ETH we have SNP. Can we find a natural class for strong ETH?
For example.
That seems like a good question to start thinking about.
Antonina?
Yeah, so I guess following up a little bit on Paul's question, so COMPAS is hard for SMP, right?
Which one? A Hamiltonian path, yeah.
Which suggests that somewhere in your mind you have some kind of lattice of which problems are harder than easier in this context.
Right.
So what would be sort of the hardest, the least hard examples in your lattice of this kind? Hardest and complete problem.
So there is, for a while I thought Hamiltonian path is such a problem until our Swedish colleagues demolished that, and I still believe it is hard for this OPP model, but I did think about the bandwidth problem for a while. I know that others are thinking about it. I don't even remember the definition. Ivan or anyone? So that may be one such problem that is SNP hard and even harder than Hamiltonian path.
I guess. So, are there like natural NP complete problems where the best algorithm is 2 to the n squared time, or anything where the power of n bigger than 1?
So this bandwidth problem, I believe n to the n. So that's what I'm shooting for. And so.
Nothing.
Of course, in the natural parameter, there are artificial problems you can cook up, and even then it's difficult.
Maybe edge coloring is a good example if you parameterize by the number of vertices.
So what's the best known algorithm for that?
I think it's more or less to the number of edges. I mean, you can squeeze that down a little bit, so it's not precisely that.
Okay, so that seems like a good problem.
I'm not sure if I got it right. So you gave some examples of implications in parameterized complexity, and I deduced from that ETH implies that fixed parameter is different from W2 or W1. So this is true. Is there anything like that for SETH or something stronger?
Okay, the way I teach it is that W1 is sort of like ETH and W2 is like strong ETH. I mean, there are ways to form like this formal.
So ETH implies that if PT is not W1 and SETH implies that,
No, not exactly. Not exactly. It's just like weighted CNF set is W2 complete.
Mm-hmm.
So like having this extra fan in it on the or at the bottom is sort of what characterizes W2. I mean, like there are like formal theorems showing an isomorphism like there are between say ETH and FPT versus W1. But there's definitely analogs you can take like results that were relating W1 and ETH and just get results like for dominating set, for example, like really W1 and CNF set.
But in terms of complexity classes, is the only implication that ETH implies W2 unequal.
Well, there is this result that he mentioned that if you can solve K dominating set, a W2 complete problems, just even a tiny bit faster than n to the K, then ETH is false. Sorry, strong ETH is false. So there's that. But, but there's no, it's not as well developed as what's known.
Daniel, you want to add?
So I will talk about this one of my lectures. So ETH implies that FPT is not W1, but for strong ETH there are specific consequences, but not in terms of complexity classes, but for specific problems. Strong ETH is consequences.
All right, well, thanks again.